So just a reminder, tonight at midnight.
If you haven't started.
Yeah. So please get started if you haven't already. Yeah, so there was a lot of questions over the weekend on the discussion board. And hopefully everyone should follow the discussion board. If you have questions, it's a good place to ask them. And if you have questions, also in the discussion board to see if they have your question hasn't already been discussed.
You're very good at answering them.
Oh, thanks. Okay, so last week we were talking about graphical models, and we're going to continue that today. And so today what we're going to talk about is when you have a graphical model. I mentioned this last time, but we'll get into the exact definition of what's called conditional independence. This came up last time. We were showing that in a chain you can integrate out or discrete sum out to marginalize a variable in the middle of the chain and then kind of just basically delete that variable and link the chain with that variable in the middle removed. This kind of came up briefly, but we didn't talk about it in detail. So today we're going to talk about it in detail. And this is section 8.2 of the Bishop chapter that is online. And yeah, so that's what we're going to talk about mostly today. We might get into a few other topics depending on time. That's the basic thing we're going to do. Okay, so in the Bishop chapter, there he goes through a series of these examples with 3 nodes in a graphical model. So 3 random variables jointly, and that basically gives you mostly everything you need to know about conditional independence. So let me write down the definition of conditional independence. So we're going to say, let's say we have a random variables, 3 random variables, A, B, and C. So 3 random variables, again, they can be discrete or continuous or kind of a mixture of discrete and continuous random variables. And we're going to have notation that looks like this. And the way to read this is that A is independent of B when conditioned on C. Or you can say A is conditionally independent of B given C. So that's the notation we'll write. Okay. And so yeah, so what does this mean? This simply means that the probability, joint probability of A and B given C factorizes as the probability of A given C times the probability of B given C. And again, I said the probability of, but again, that's, depending on discrete or continuous, that might be a probability mass function if it's discrete, or a probability density function, which is not a probability in itself, it's continuous. Okay, and of course, this mirrors the definition of independence, right? If I just didn't have this given C in all 3 of these probabilities or these PDFs, it would be the definition of independence of A and B, right? So the only thing we do when we talk about conditional independence is we take the definition of independence and add a condition to all the probabilities involved. Okay? Question, yeah.
If C is the universe, then I think I'm correct where
Yeah, so,
independence is correct.
yeah, I mean, okay, so, yeah, typically I would be a little careful that, yeah, I guess you could say that, yeah. If you had a random variable that was just always true as C, then yeah, then this would reduce to independence, yeah. So in some sense, yeah, it kind of subsumes independence as a part of the definition. But yeah, interesting case, of course, would be when C is a non-trivial random variable where it has some probability of being different values, of course, yeah. But yeah, you could kind of say that, yeah. But this subsumes the independence. Okay. Any other questions about the definition? Okay. And you can verify. It's fairly easy to verify that. If I take this P of B given C and divide it over on this side, that is equivalent to saying wait, sorry. Let me be careful. Yeah, this is right. Yeah, that's equivalent to saying this. Okay, and again, if I delete the C from this side and that side, it's again the equivalent definition of independence without an extra of A and B, right? And so and likewise, I can get the kind of third definition of conditional independence. Again, just mirroring what you get in independence. You just kind of add this C on the right-hand side of the condition. And all three of these things are equivalent. Again, ignoring, assuming that C is not some value that has zero probability, of course. I'll always have to assume that the things on the right-hand side have non-zero probability in the discrete case, because then you couldn't divide otherwise. But yeah, these are three equivalent definitions of A and B being conditionally independent given the random variable C. Okay. Right. Any questions so far? And let's be very careful to think about what we mean by this condition. Remember, conditioning, one way to interpret this is if I observe a value for C. Okay, so think of things on the right-hand side as random variables which have been observed. Okay, so if I have something on the right-hand side, it's a random variable. We have probability distributions of it and everything like that. But what I mean here in practice is that it's now to be pinned down to a specific value because I'm observing that random variable. Okay, so you very often will see kind of a notation, probability of X, given Y equals some value. Let's see, don't use C again, but let's say
Just put a number.
3. Yeah, that's true. Yeah, Y equals 3. There you go. Yeah, next. Yeah, feel free to suggest me when I get stuck in things to write something. Yeah, so P of X given Y equals 3, for instance. So you'll very often see this notation that given a random variable evaluated or was observed to be some value. So when we write this notation, it's really kind of shorthand for there was some observed value for C, but it's kind of generic when we write it this way. Okay. Okay, so I think what we'll do next, unless there's any other questions, is we'll go through the three different configurations of just 3 random variables in a graphical model. Okay, and this is again in the question. Is there a question?
Is it something related to A and B are independent?
Say, this is we'll see here in a second. It's This is a related concept, but it's a different concept. So the situation could change if I take C out of the equation. So in all of these scenarios, you can consider what is the relationship between A and B if C were not even in the picture, so not conditional C. And we'll see in a minute, the answer changes depending on the way the random variables are distributed jointly, okay? And yeah, so this is that's a great question to bring up. This is distinct from independence. So A and B, if you know the conditional independence, it really actually doesn't tell you whether A and B are independent of themselves. But if you know the graphical model that explains how the joint distribution breaks down, you can actually say something about whether they're independent or not. We'll see here in a second, yeah. Okay. So yeah, so let's take a look at some examples, or these 3 examples, and it'll get to your question. Okay, so example number 1. Looks as follows, and I should mention these 3 examples are you could rename all the variables. To make A, B, C and read them, like cycle them around and change the labels. But the question is, how is the graph structured? And so there's basically 3 types of graphs we can get here. So I can have the following graph: A, C, and B. And again, you could commute all these A, B's, and C's, but the point is that you've got one node in the middle that kind of has spokes going out to the other 2 nodes. Okay, that's the first structure we're going to look at. And so remember from what we said about the meaning of these directed graphs is that this means that we know that the joint distribution breaks down as each node is conditioned on its parents, and then if a node does not have any parents, then you get just in the factor, you get just P of C by itself with no condition, right? So this graph tells us that the joint distribution A, B, C is equal to P of C, which has no parents, times P of A given C, so A has one parent C, and then B is the same, P of B given C, right? So, so as you're reading the Bishop chapter and then also the Murphy kind of notes on the web, by the end of all this, you should feel very comfortable reading a graph and saying, oh yeah, that's what the factorization looks like. So this should become like second nature, hopefully, eventually. So anyway, that's this graph. Everybody happy with that? And so the question is, what are the what does the conditional independence look like here? So yeah, so actually let me bring up, so kind of getting to your point, if I'm just talking about independence of A and B, we'll have this similar notation. We'll just say A and B are independent by saying this. So A, B independent. Alternatively, you could write A and B are independent given kind of null, no other information. Conditional on nothing. In other words, they're independent. Okay, so I think you see Bishop uses this, says this somewhere in the text. But either of these this is just a little short. A is independent of B, no condition. Okay, so yeah, so the question here in this graph, if I have this factorization of the joint ABC, what can I say about, first of all, are A and B independent given no condition, no knowledge of C? And then what can I say about A given B if I do conditional C? So the picture, just to kind of keep in your mind, is that this is, C is a circle unfilled circle. So this means you're not conditioning on C. There's no given here, right? Now if I fill in this circle, and I have a picture like this, this is the case where I am pinning down. Remember, a filled-in circle means you've observed that random variable, and so now I'm really conditioning on C. Okay, so in all these examples, 3 examples we do, there's going to be kind of 2 versions. One where I don't condition on C, don't observe C, and one where I do observe C and condition on C. Okay. So the first case over here, let's look at I don't condition on C. Okay? And what I want to do is I want to check are A and B independent. So remember, this means that A and B by themselves, their joint distribution would have to factor to just P of A times P of B. Right? And so this is the thing we're testing for independence. And this is the thing we'll test for conditional independence. So let's first take a look at independence of this graph, A, B, I don't observe C. So how do I get, again, let's assume for simplicity everything's discrete. How would I test this independence question with this picture so far? Anybody? Did anybody read Bishop? Yeah.
It looks to me like A and B are conditioning independent of C.
Okay. But we're not doing that yet. You're jumping to the second case. You're right. We'll get there. but before we get there, and it's actually easier. The conditional independence is easier to see directly. The independence is a little harder to see. But we're going to do the independence. The question of independence, I should say, is harder to see. But how would I go about checking this independence rule? If I know this is all I know about my probabilities between A, B, and C so far. How would let's say C is discrete, and we'll take a finite, let's say even number of discrete values. How would I check this? How do I make this left-hand side P of ABC turn into a P of AB? Yeah, marginalize, right? So I'm going to marginalize over C. So just if I take both sides and sum over all possible C values, then the left-hand side just becomes, so I'm going to sum over all possible C values. I'm leaving this summation notation kind of vague here. I'm not saying what C takes on, it's just whatever values, doesn't matter. We're assuming discrete for the time being. If it was continuous, of course, I'd do an integral. But yeah, just sum over this, and that is just the marginalization equation. This is equivalent to P AB. And so this P of AB is going to be equal to this side summed over C also. So now I'm going to write this right-hand side with a sum over C. Like so. Okay? And now, to test independence, the question really is, does this expression, because it's equal to the joint P of A, B, does this expression factor into a function of just A times a function of just B? Okay? Can anybody tell me, can I factor this into 2 separate functions of just A and just B? And no, you can't, right? So the C is intertangled, right? That's not a real word, but it is kind of tangling the P of A and the P of B together. There's no way to split this into a separate thing. Okay? Now, I should say that is, you have to be a little bit careful. There are some distributions where I could write this down, but in general, and make it split. But in general, if all I know is that my joint PDF factors this way, then that doesn't tell me, this is still an open question, that this does not really necessarily factor into Feifei and PV. Okay? So if I write a graphical model this way, it doesn't tell me that A and B are in general going to be independent. Okay? Is everybody convinced from this expression that in general I can't write this as a, let's say, F of A times the F of B, G, B. Okay? Now getting to the question of conditional independence. How would I test if this expression is true? Yeah.
Second and third equations, I have a quick question on that.
Okay, go ahead.
If the second equation was, yes, if it was P of A given B and C, if it was equal to P of A given B.
Sorry, so it's P of A and?
Can I read it as if C is given, I have no new information on, suppose if it was P of A given B, I would be more comfortable.
If there weren't C?
Yeah, on the right hand side, if it was A given B,
Or given B? Oh, okay.
I would read it as if I condition it on C, I would get no new information on A given B.
Right. Yeah. Yeah, I could rearrange this if that helps. And then you just have to rearrange your alphabet. So if I know B, it doesn't give me any further information on the probability of A given C. Right. Yeah. That's
the
right.
same.
Yeah. I know what you mean. It's yeah. But yeah, and the same thing if I just deleted the C, it's what we usually say in independence, is that knowing B gave no further information about the probabilities of A, right? And in this case, it's saying, if I throw in a C here, then throwing in a B doesn't give me any additional information about the probabilities of A. Okay? Yeah, so these are, important expressions to kind of think through exactly that way, make sure it makes sense intuitively what we mean by this. And we'll do some intuitive examples here in a minute that are just, we won't go through the numbers. I think the numbers you should go through carefully in the book chapter and the one on the web page there to help this really sink in. We'll go over them intuitively, but we won't do the arithmetic on the board. I'll leave that for everybody to do it in. Okay. Okay, yeah, so how would I check? We can check any one of these three equations. What would be a strategy given I know this factorization right here? What would I do next to make that look like one of these equations? I'll give you a hint. We want to probably focus on the top equation. I mean, they're all equivalent. The top one's closer to what we want to look at.
Well, we can start with the left-hand side because we are given C already, right? It's not a joint in all three on this right-hand one. It's given C or the right one.
The right-hand one.
Because
yeah,
it's
these are
still
already,
there.
exactly.
So it's already A, B given C.
Exactly. We already have these two expressions in the factorization. P of A given C, P of D given C are already here.
Right.
Right? And what's the one thing over here that we want to move?
It's P of C.
P of C. So we just divide both sides by P of C. if I do that, everybody hopefully recognizes this is just what? Yeah, exactly. It's what we want on the left-hand side there. So this is equal already to T of A and B given C. That's just the definition of that conditional probability. And again, assuming that, you know, the value we observed in this discrete kind of case here, the value we observed for C happens, so it doesn't have probability 0, so we didn't divide by 0. Then in that case, this equation works out to this. And so what we get is, yes, it is the case that A and B are conditionally independent given C. Okay. But as we saw in the first example, no, A and B are not independent in the unobserved C case there. Okay? I should actually mention this notation actually means that this holds, to be very careful here, that this holds for all possible values of C. So if one value of C breaks this equality, then they're not conditionally independent. So conditional independence doesn't mean there's some values of C that will make these two things factor out. It means that no matter what I pick for C, if I observe C, no matter what it is, it will break it'll factor the conditional probabilities this way. Okay, so that's an important point to make. This is kind of an important piece I was leaving out there. Okay, and this works because no matter what I observe CB, algebraically this is the case if I can write the PMF that way. Yeah.
So the P, A, B, C, this equation is for which of the graph?
Say again.
The top P, A, B, C equation is for which of the graph?
This is the equation for both graphs. The shading really just means that we are going to now treat C as an observed random variable. So the actual these conditional distributions are really represented by the arrows, because this conditional distribution is really just a formula. No matter what C you plug in, it's saying that this is the way this thing factors. Okay. The shading notation is really kind of for our own convenience to kind of just say whether we've observed C or not observed C. Okay, so any other questions about this example? Let's see. I'll come back to this example if we don't run out of time. If we do, I'll do it on Thursday, but I'll just kind of throw this out there. We'll come back to in a minute. We've already kind of seen this graph. We haven't seen the graph, but we've already been using this property in our earlier topics, because if you think about when I have a Bayesian model, let's just do Bernoulli for instance. If I have a Bayesian model that says the theta parameter in Bernoulli has some prior, we talked about the conjugate prior beta prior, and that's 1, 1, it's a uniform prior, and then my observed data xi, given this parameter is Bernoulli, so just binary random variables, probably theta 1. Then what does the graphical model look like it looks like I have a node for theta, and then xi is conditioned on, oops, I should have a circle there. Xi is conditioned on theta. It is typically, the data that we observed. And there's more than one xi, otherwise, typically, right? So I've actually got, let me draw it, not with plate notation for the time being, but I would have something like this. So I have n of sort of data, which remember, I can draw the plate notation to kind of simplify that. It would look like this. And repeats that kind of, right? Now notice, this is exactly, it's maybe more than 3 if you have more than 2 data points, but with 2 data points, it's exactly this graph. And this is, we see this exact structure where we have one node where things, errors emanate out from one node. And now notice, this condition here, this conditional independence condition, is saying that given theta, my data's IID, right? And that's the general assumption we make in statistics, is that we have IID data. If you're a frequentist, you don't condition on anything because theta is just a constant. It's this kind of magical constant of the universe you don't know and you don't observe. But if you're a Bayesian, you say that this is a random variable, and then technically your data is not IID unless you condition it on theta. So the likelihood is x given theta, and that's where the breakdown, x given theta, that's where the IID assumption comes in. So it's really, there is a condition, obviously, in Bayesian likelihood that this theta is random. Okay, so we've already seen this picture. We've already seen exactly this independence. What we've really been doing with IID is really conditional independence. Okay? I'll come back to this in just a minute, maybe, in just a half hour maybe. And we'll actually crank through a quick calculation to see what this conditional independence, how we can think of it in terms of predicting an unseen value. Okay, and why it's not independent, it's actually conditionally independent, and why that's makes a difference. Okay. Let's see. Yeah, I'll just make a mention, and this is in the Bishop chapter also. This particular structure of this graph is one that we see in a classifier called naive Bayes, which if you took machine learning, you've seen the naive Bayes classifier. This is what the naive Bayes classifier looks like. So you have, I can really just write it with a slightly different notation. C, so the class label, it could be 0, 1, let's say, classifier. And you have a vector of observations, and what you do is you say that each element, each one-dimensional element in that vector is, I'm going to have an independent classifier for each element in that vector, and then my joint classifier for everybody together is just going to be a product of the individual one-dimensional classifiers, probabilistic classifiers. And then if you're Bayesian, you put a prior on the class label. But anyway, that's, if you see naive Bayes, it is exactly, again, this kind of picture, where instead of these being different samples, these are now different elements in the vector. That is a single feature vector for what we're trying to look at. So anyway, that's another place that this graph structure comes up in machine learning. Okay. All right, moving on to the next configuration. we saw last week, the Markov chain. So you can have a chain of random variables. Let's say C staying in the middle here. So it's a little bit, again, you can permute your alphabet if you want. But just to stick with the notation that C's in the middle in all three examples. So now I have a chain ACB. And same question, in this case, are A and B conditionally independent given C? And question, are A and B independent with no observed value for C? Okay, so, and again, that's the difference of shading in C or not. Okay? Now, again, in this picture, this is saying that the functions determining the joint distribution of A, B, and C factors as, again, remember, P of A has no parents, so it has no condition. C has A as a parent, and so C given A. And then B has one parent, which is C. So just intuitively, as your gut reaction, if you think about A and B, are they going to be independent or dependent? Just think of this as like a flow of information, these arrows, these conditional distributions. Yeah, dependent, right? Because A influences somehow C, and then C then influences B, so there's some kind of information flowing from A to B there. And again, we can convince ourselves that that is actually true. If I sum over C here, well, yeah, if I sum over C, we know this is going to be P of A, comma B, and then this side summed over C, P of A, P of C given A, and P of B given C. Oops, I should put parentheses. Notice I can pull P of A out of the sum, and so it's easy to see here that, again, in general, for these to be independent, I would need this term here to reduce to P of B, because I've got a P of A outside there. And of course, that doesn't work.
Right, but couldn't we convert this Markov chain into example number 1 using the same method we had to take out a link in the chain?
No, remember, when we took out a link in the chain, what we showed was that
take the link out.
if you sum over C here, so marginalizing C, we showed last time, summing over C actually gives you this model. If you sum over C. And this directly shows you, so the computation we did last time shows you directly that this actually is dependent in general. That B given A is in there. Yeah. And yeah, we could have done that. Remember, this actually we did last time. This reduces to P of B given A times P of A. This term here, let's see. This we had a combinated here. You could reduce this to P of B given A. But that required the step that which I'm going to show you next. Putting an A in here requires that is exactly this, right? And so what I told you last time was that we snuck in an A here, and I said we can do that because there's conditional independence, which I will tell you about next time. So actually what we did last time was not a real proof because it depended on the step that we're going to do now. Yeah. But without that, you can see that there's no way this is going to reduce to P to B. There's no, that it's not independent here. Okay. Okay, so yeah, so what we did last time, right, to show that this A, that you can delete the chain link C and basically connect the chain directly to A and B, we did sneak in an A here, which was really showing conditional independence. Let's see, what was it there? Right, it was showing that it was exactly this equation we have here, and that's what we're going to prove. This equation does hold for this factorization here. Okay, so yeah, so how do we do that? Again, let's see, this one.
I have a question.
Yes, go ahead.
In first example, if C is not given, then we cannot comment on independence.
That's correct, yeah. If C is not given, you can't say anything about independence. So let's think about that again, just real quickly. Yeah, I mean, I think that's right. I think that's yeah. That's basically if I don't observe C, then A and B are not guaranteed to be independent. Yes, that's the way to say it. Yeah. I'm trying to think of an intuitive example. Yeah, I think the.
So there's one example that helped me kind of grasp this. Say this is like a pseudo-random number generator, and C is the seed.
Okay.
Give the number generator, and A is the first number it generates, and B is the second.
Okay.
So if you know the seed, then you know, like A is the first number. You know what A is going to be if you know the seed. You also know what B is going to be if you know the seed, because it's just the second number the generator will produce.
Right.
But if you don't know what the seed is,
that's a good example. Yeah.
then A will be random. But if you know A, then you also know what B is going to be, because it's just the number prior to B.
If I don't observe C, hold on a second. So if I don't observe C, I mean, that's a good example with the caveat that pseudo-random number generators aren't really independent or.
Right, but if you have a random seed,
yeah.
then A and B, your first two random numbers, are random. If you have a random seed. Right?
But what does that mean to have a random seed?
Say your seed is a random variable that's coming from some external
Okay, so
source.
it's something that we take to be random, like thermal noise or something crazy. Yeah.
Then your first number out of your random number generator will be indeed a random number.
Okay.
And the second number will be a random number too, but it's conditionally dependent on the first random number.
It depends on the process.
Boy, they have to be careful. So,
Right.
so
This is
conditioned on C. So if we assume that pseudo-random number generators. See, the thing is that we're saying conditioned on C, this random seed, that A and B would have to be independent. First of all, I think pseudo-random number generators break that. There's not a random number generator that actually gives you independent, even conditioned on seed. But if we assumed it did.
Like if you're given a seed, you always know what the first value will be. And you always know what the second
Right,
value
those are
will be.
deterministic.
Those are deterministic.
Sure.
And that's what I'm saying.
Okay.
But A and B are deterministic, knowing what C is.
Yeah.
Then they are not independent.
But
So
see
they're not
that.
independent.
Yeah, I know, and that breaks
This is
this.
They are independent if you know what the seed is.
But I think they're not. I think we should stay away from pseudo-random number generators. I want to be careful because I think we have to be very careful because pseudo-random number generators, the pseudo there is the important word there is that they don't actually behave like random numbers anyway. But I think I get your point. Something along those lines. But we have to. I want to be careful with pseudo-random number generators.
Okay, so let's take another
it gets into a big discussion Because they are deterministic, they basically are deterministic. If you know the C, nothing's random technically. So this all blows up if A and B are not random anymore once you observe C, so that doesn't fit this. But anyway, yeah.
The popular example for this is there's a company producing night lamps, and the
Okay.
kids were sleeping and they grew up to be myopic patients. So
Okay.
the myopia versus night lamp A and B,
Production.
and you condition it on what? So if you can condition it on the parents being myopic or something like that.
C's parents being myopic?
Yeah.
But C would have to somehow, you'd have to condition night lamp production on parents being myopic, right? So how does that work? Okay, maybe we should steer clear of intuitive examples. I think one intuitive example, although I think it also possibly breaks down, that I was thinking along these lines, but I stopped myself because I think it also breaks down. Anyway, if you think of this as this is some type of disease or ailment, and then symptoms that you get are conditioned on that, on having that or not. So, for instance, the example of I have the flu. You could have A, B, I have a cough, and B, I have a temperature. Okay. So the problem is that it's hard for our brains to think about. I think if what does it mean if I have the flu for these two to be independent? Because you kind of just get both usually. So anyways, that's a hard example. That doesn't quite help. Yeah.
Isn't in some sense that beige and, well, the intuitive argument that beige that we're playing billiards, you throw down the cue.
Yeah, there you go. That's a, and this might be your random number generator. So yeah, let's modify your random. I was trying to make your random number generator work. I think this is the example that makes it work. Okay, so let's do this. Yeah, that's great. Thank you. So Bayes, remember his thought experiment for exactly this model, where this is he was doing uniform from prior, was you throw down a billiard ball on a, I would say pool table, and where it lands horizontally, let's say on the pool table, is theta from one side and 1 minus theta from the other side, and then all the other balls you throw down, one ball maybe at a time you throw down. Those are the x's, and they're binary. Let's see, they are, say probability theta landing on the theta side, and probably 1 minus theta landing on the 1 minus theta side, so you can call that a 1 and a 0. And that's kind of this generative model. And let's see, so then to think of conditional independence, one way to think about it is as follows. So this thought experiment I'm doing in kind of my game room with the door shut, and I'm just telling you the results through you can't see my pool table, okay? So through a microphone or something. So anyway, I throw down the ball, and I tell you that ball came out to be a 1. Okay? But I don't tell you anything about the theta. I'm telling you about the X ball that the first X ball. And then you were asked, well, I'm going to throw down the second ball. Do you want to put a bet that that second ball is going to be a 1 or a 0? And what would you typically bet? Given no other information. You would bet 1. Because the fact that you observed a 1, obviously there's not much information to go on, not much to bet on. But if you have to be forced to bet on it, 1 or 0, you would pick 1 because you don't know what this theta is. The chances are that it is, that it's a wider theta than 1.5, given just that one observation. We could extend this. I gave you 10 observations. I said I threw down 10 X balls, and 8 of them came out to be 1s, and said, and I'm going to throw down the 11th ball, which do you want to bet? That's a 1 or a 0. Then you would say, okay, yeah, definitely I'm going to bet 1. If 80% of the balls came out 1s, then I've got, if B is the 11th ball, it's not independent of the first 10 balls I threw out, right? Now, if I tell you I've thrown down the theta ball and it came out to be 0.8 distance from the side, then you don't care if I tell you the X balls or not. It's completely irrelevant to you. You don't need any other information. And that's telling you that these 10 balls I'm going to throw down are independent of the 11th ball if I give you the theta information. Okay, so that's a great example. Thanks. I mean, it's exactly the example I was going to do with the prediction here, but I didn't think about it in terms of the actual pool table. It makes it really clear. Yeah. So we're going to, now I'm starting to think we'll do it on Thursday, but we'll actually do the posterior predictive model and look at the exact, what the numbers or the equations come out to be that say exactly this in terms of math, but I think it helps to think of it in terms of the pool table example. Actually really nicely illustrates it. Okay, cool, yeah. Okay, right. Okay, so moving on, I do want to get through all 3 examples, so we should probably keep going here. Okay. Okay, so long story short, coming back over here, we have currently that A and B are not independent, or we can't say that they're independent, given the middle of their information about C. Okay. Okay. Now, let's look at the conditional independence. We're coming back to do conditional independence. So how would I try to get this equation again up here? This one's a little bit trickier. So I want to get this equation out of, starting from here, and get it here. So try to get there. So again, if I just look at the left-hand side,
We can say plug P of A and P of C given A.
P of A and P of C given A. These
And
two.
we can write P of C, P of A, and C.
Uh-huh. Right. Okay. Yeah, so this P of A times P of C given A is the joint P of A and C. Yeah, exactly. So so I can write it, I can multiply those two together and simplify it like so. And now, and you're saying now factor out A given C times P of C, and that's just, all we're doing there is Bayes' rule. So I'm gonna, and then what I'm gonna do, I'm gonna skip one step ahead of you, then divide out the P of C from that. And we get on the left-hand side exactly what we did in the other case.
Or you could just divide by P of A and C and you get that second equation. Or the third one.
P of
P of
A,
given
yeah, right, A
and
given C, or A.
If you divide by the P of A and C, you get that third equation.
Yeah, you're right, yeah, exactly. If I divide both sides, yeah, that's a good point. So, yeah, if I just divide by P of A, comma C, A, comma C, yeah, I get this third equation. Yeah, that's a quicker. I was going to get this one again. If you divide by P of C, you get exactly this. If I divide by P of A jointly, A and C, I get this. And of course, I have to be careful. I think actually, to be very super careful, we would just divide by P of C because if observed, we know this is not 0. If you observe C, in our case, we're conditioning on C. But yeah, you can do either if you make assumptions about that you will not get a 0, probably joint probability. But this one definitely works no matter what. And we get just that equation. Okay, so in the end, what we see is that, yes, it's the case that A is conditionally independent to B when we observe C. Okay? Any questions here? So what's the intuition here? If I fill in the C, then the information that A was passing to C is no longer needed because I already have C, so the direct conditional going B is there, and I don't need A's information being passed along anymore. Is one way to think of this information flow through the graph. Okay. Right. I think what I'll do is the last one takes some time, so I won't dwell on this one much more. The third one, let's see. I'm going to try to let me erase over here. Pretty sure we're not getting to the example here, but I'll leave it up just in case we wrong. But let's see, number 3. Looks like so. So all of these examples, by the way, are ACB with errors between A and C and C and B. It's just a matter of which way the errors are pointing in all these cases, right? This one is a little bit trickier to think about. Let's write down what this means first. So now I've got 2 nodes that don't have parents. P of A and P of B factor out like so. And now C has 2 parents, both A and B. Okay? Now notice, if I do the same trick we've done in the other 2 cases, I marginalize over C. We're going to take a sum over C here and a sum over C here. The left-hand side is the same that we've done in the other 2 cases. Summing over C just gives me P of A, B by itself. And now the sum over C here, I'm going to bring inside because these don't depend on C. So I get the sum over C of the last term, which does depend on C. And who can tell me what is this equal? Yeah, 1. I thought that was a hand up. Yeah, that's a 1. Yeah, exactly. So yeah, so this is P of A times P of B. So remember, a conditional density, or rather a PMF, if you will, it really only depends on what's over here. It doesn't matter what we have in the condition. It's still a probability. So if I sum over C, the only thing on the left hand, the conditional, then it's a probabilistic sum. Okay? And so this is directly equal to our independence conditions. So we see right away that A and B are independent in this case. So I don't observe C. I just marginalize C out. No matter what, it's A, B, or independent. Okay? So given that A and B are independent, who wants to take just a quick guess? If A and B are independent, do you think they're conditionally independent if I do observe C? This will really test people over your guesses. So you think they're going to be conditionally independent if now I observe C? So I'm getting take as more evidence than my Bayesian post here saying that most people haven't read the book. Okay, that's fine. Yeah, so, okay. So let's do the calculation. So again, we want to check, is this rule holding up or not? Okay, and essentially, the argument is that if I divide by C here, again, as we did in the first case with the independence, there's really no way to factor this left-hand side into something that looks like a P of A given C and a P of B given C. So if you divide both sides by C, the left-hand side will be what you want. The right-hand side is going to be kind of this jumbled mess, divided by C, and nothing really factors out there. Again, this term really can't be pulled apart, so it has just an A or just a B in it. And is everybody clear on that argument? Is there any questions there? Without me writing it down. Okay. So what we see in this case is that no, A and B are not independent conditioned, or not conditionally independent given C. So what's interesting is that two things that start out independent, they lose that independence, which is kind of a counterintuitive concept. They lose that independence if you then observe a third random variable C here. They no longer are independent. Okay? And with the interpretation of independence being conditional independence, they are still independent, but not conditionally independent. So what does this mean? I think now intuitively, the examples from both the book and the Murphy notes on the web kind of help us think about what are some scenarios where this type of thing can happen. Okay, so again, I strongly recommend, I'll just read that there for all see. I strongly recommend going through these examples in all the arithmetic gory details because you really need to convince yourself that this can happen, that you can lose independence by observing another random variable. So it helps to see it in the numbers. Okay, but let's just quickly look at the examples just and think of them intuitively what are kind of these examples. So one example, I'll do this one first, and I'm going to simplify it a little bit from what Murphy does on the web page that is linked. He actually has a fourth random variable, but I'll make it a little bit simpler, simplifying assumptions here. He has one random variable is, these are all binary, so one is it raining or not raining? The other random variable up here is have my sprinklers run or not run? And then the third random variable is the grass wet or is the grass dry? So one if it's wet, 0 if it's dry. Okay? Now, the conditional distributions here are pretty high probability if I observe it's raining or it did rain, let's say, whether it's raining currently or just rained recently, with a high probability of the grass being wet. If my sprinklers have run recently, again, a high probability of the grass being wet. And notice if I were to integrate out the grass being wet, marginalize the grass being wet or not, and just ask you, this is where I have to remove that other random variable because that linked these two. But let's assume a simpler case and just ask you, is rain and my sprinklers running, are they independent or dependent? And you have to assume that there's no human watching the weather forecast, and you have to assume that there's no like sensitive, the sensors on my sprinklers that will stop them from running if it's raining outside. So ignoring those, let's say the sprinklers are kind of on their own timer, and I'm on vacation somewhere warm, and I'm not paying attention to my sprinklers. Yeah, so anyway, given those conditions, we would say the raining outside, if it starts raining, that doesn't affect my sprinklers, and my sprinklers start, that's not going to affect whether it's going to rain or not. So those are two really independent probability things. And I'm going to just say, if I had to bet on whether it's raining or not, I would just go with the probability of rain here in Utah, and I wouldn't, ask you whether my sprinklers are running outside or not. And then vice versa, if I had to bet whether sprinklers are going or not, I would just go with, what is the frequency at which my sprinklers are coming on, and I wouldn't ask you is it raining or not, because I know my sprinklers are on autopilot and don't have a sensor, let's say. Let's say I'm a bad water conservationist. So anyway, that's if I don't observe whether if I don't observe the grass being wet or not. Okay? Now, this is the tricky one, and this is where you have to think these through, and I think go through the numbers very carefully to see how this works. If I observed, I called home from vacation and asked you, hey, is my grass wet outside? And you said, yeah, the grass is wet. And then I had to bet whether it's raining or whether my sprinklers are on. First of all, I would increase the probability that yes, it is raining. I'd also increase the probability that yes, my sprinklers are on. But think of it this way: are these two now related? And actually, they are. So why are they related? If I tell you it's raining outside, now are you going to increase or decrease or keep the same your probability that the sprinklers are on?
Usually decrease.
Say it again, decrease.
Usually decrease.
Yeah, you want to decrease, exactly. So this picture, I already increased my sprinkler chance by the wet grass. But then if I tell you it's raining, I'm going to say, oh, I'm going to bring my sprinkler chance back down because rain has explained maybe why it's wet. So I'm going to decrease my probability that the sprinklers came on. And vice versa, if I told you it was wet, my grass is wet, you would say, well, the rain now has a higher probability just by applying Bayes' rule. I could get that. But then I add the information that no, but your sprinklers went off. Then you're going to say, let me bring back down the probability of, maybe not all the way back down to baseline state, but I'm going to bring back down the probability of rain because the sprinklers may be explaining why the grass was wet.
Or if you know that it did not rain, then your confidence that it was the sprinklers shoots up even higher.
Yeah, now there you go. Flipping it is actually better. Yeah, you're right. So now if I know, I observe that, and let's do it this way. If I know that my sprinklers did not, so this is observing, it could be 0 or 1. Yeah, let's do it the other way. If I observed, or you told me that my sprinklers definitely did not go off, and the grass was wet, then your probability that it rained is going to shoot up much higher. Yeah. Or some other weird weather phenomenon might. Maybe there's not 100% probability. Maybe there's a lot of dogs in your neighborhood that walk into your grass. So you don't know exactly it's rain, but yeah, you want to really increase that probability. If you know this is 0, this is 1, this is much higher probability. Yeah. So by observing the wet grass, you've actually linked the probabilities. They've become dependent on each other, the rain and sprinkler. So one other example that's in the Bishop book, which I think Yeah, I'll just mention, so rain and sprinkler, the Murphy example has this fourth random variable cloudy. And this is basically just the probability of a cloudy day or not a cloudy day. And so that kind of complicates the picture, but it's still a worthwhile example. Actually, if you go to the Wikipedia page for Bayesian networks, let's see, they actually have a good sprinkler system where the rain changes the chance of the sprinklers coming on or not. So the sprinklers have some kind of sensor in them, presumably, or at least a conscientious person turning off the sprinklers when it starts to rain. So anyway, yeah. But then the Bishop book, just as another kind of intuition example, which I think is a good one to go through. He has a car where you have a binary random variable is your battery, your car got charge in it or is it gone dead? The fuel tank, is it gone empty or does it still have gas in it? And then the third random variable is the fuel gauge. So if your battery goes dead, the fuel gauge will go down to empty just because it needs electricity to read the right fuel level. And if your fuel goes empty, of course, your fuel gauge will also go down to zero. Either one can cause your fuel gauge to go to zero. Is the point. And so it's the same situation. Exactly, same situation with rain and the sprinklers and the grass. So anyway, this one, I definitely make sure you go through this, think about it carefully, because it's going to come up. This is called a, by the way, a V structure. Or also sometimes called like a head-to-head nodes there, or at least because the arrows are head-to-head this node. So, long story short is that this is the counterintuitive configuration of three nodes that really does take, I think, some thinking about logically and both, and also working out the arithmetic of how this conditional, this is the one case where the conditional independence fails to hold, but strangely enough, the independence marginalized CL does hold. So it's very important to go through that example. Okay. In the last few minutes, first let me ask, are there any questions at this point? Okay. Last few minutes, I'll mention one last thing in the conditional independence chapter, and this is where these little small examples actually tell us how to read a much larger network about whether or not two random variables or even two sets of random variables are dependent on each other or independent of each other. And so I can take very complex networks, very complex models, and read off the graph just visually whether or not two random variables are related to each other. Are they independent? Are they conditionally independent? I can get this directly from the graph. And this is a concept called D-separation. Oh, I did need to make a historical comment here. So a person who's really credited with these Bayesian networks was Pearl, who hopefully the computer scientists in the room know was the Turing Award winner. I think in like 5 years ago, I think 2011. And he won
Bayesian networks?
Bayesian networks, yeah, the guy that came up.
So the Turing Award was for Bayesian networks?
Amongst other things, yes. So Bayesian networks are really big in artificial intelligence, and you have lots of other artificial intelligence contributions. And another one was the idea of causality. And so he is famous for that. So Bayesian networks, if you believe Turing awards are important, are good things to know. For those of you that aren't computer scientists and don't know, Turing Award is like the Nobel Prize for computer scientists. So he won the Turing Award for his invention of Bayesian networks, and kind of he came up with a lot of these properties, conditional independence properties. And also another guy, Dawood. They're both referenced, by the way, in the Bishop chapter. So there's a few references to Pearl's papers and Dawood's papers. Dawood did a lot of work defining these conditional independence properties and D-separation. I think was maybe Pearl. Anyway, so if you want to read into some of the like original literature, follow those references. These two guys that are in the book. Pearl has really several important books, but one book that's I think called Causality, explaining how this is the point I made last time, that probability actually can't tell us anything about causality, and the reason the first person to kind of explain that was Pearl, and so. Okay, so we'll get to D-separation next time, but just let me just leave you with the causality example that I think is really, and again, we won't go into this into detail, but if you want to read some of Pearl's work, that's where you would get more out of it. So there's kind of this one example, smoking, we think leads to lung cancer. So we would typically write our graphical model this way. Again, these could be binary variables. You would not write the graphical model this way. You would not think that cancer would somehow give you the desire to smoke, right? So that's not how we would typically write this model. But in terms of probability, that is a fine way to write it. This is really injecting our idea of what the direction of causality is. And the way we would make inferences. And so what Pearl said is the only way to really decide causality here is not through probability, retrospective probabilistic analysis of data that cannot tell you this. What you would have to do is you would have to actually be able to change these variables and then see the effect on the other variable. And so the way to think of this, just as a thought experiment, is if I were to force somebody to smoke a lot, I would increase my chances that they would get cancer. And vice versa, if I were somehow able to give somebody cancer, that would not influence my probabilities of whether they're going to smoke. So affecting one random variable can, being able to force one random variable one way can tell you how it's going to affect the other random variable, but you have to be able to do this at the experimental design. You can't do it after the fact in analysis. So you can't really get at causality of which affects which by analyzing the data after it's been collected. You have to actually be able to set up the experiment and be able to change the random variables. So that's kind of the idea behind causality that Pearl came up with. Anyway, we're out of time. Okay.